Welcome to the second video on hashing. I'll simply continue from where I had left off. First, I'll start with the definition of collision. You can just pause the video for a moment and go through it. So I hope you have gone through the lines that you can see on your screen. So collision is defined as the situation where more than one key value is mapped into a single location of the hash table. Now remember, whatever the hash function is used, the complete removal of collision is impossible. Also, collision in hashing cannot be ignored, whatever be the size of the hash table. The most interesting question that now arises is what to do if there is a collision. Now, there are several techniques to resolve collisions, and two important techniques are listed below. The first one is closed hashing, which is also known as linear probing, and the next one is open hashing, which is also known as chaining. So using these methods, we can come up with processes where collision can be resolved. Now I'll discuss closed hashing. Let's discuss closed hashing. The simplest method to resolve a collision is closed hashing. Suppose h is the size of the hash table. If you remember, in the previous video I had discussed about this term h, where I had said that h should be a prime number or a number without small divisors because it minimizes collision. Now it can happen that the size of the hash table is same as the value of this term h, and it can also happen that the size of the hash table and the value of h differ. Now, how does closed hashing work? If you can look at the algorithm, I'll try to explain what this statement actually means. So let's say you start with the hash address where the collision has occurred and you call it I. Let's say collision occurs at a particular point at a particular index, and let's say that index is index I. Now, if you're employing closed hashing, what you will do is you will follow a sequence of locations in the hash table and carry out linear search. So what you will do is, this is the point of collision. Now you will look for the next location. You will carry out a sequential search. So you will look at the next location, which is I plus 1, which will be followed by I plus 2, then you will go to I plus 3, and so on. Now, while carrying out such a sequential search, the following three cases can occur. Now, what are these three cases? The first case is the case which corresponds to successful search. So if the key is found, that means the search is successful. And the last two cases, so I'll just write it for you. The first case, it corresponds to a case of successful search. So it corresponds to a case of successful search, and the last two cases that you see here corresponds to unsuccessful search. Now what happens is the hash table is considered to be circular. Please keep in mind that in closed hashing we will assume that the hash table is circular in nature, so that when the last location is reached, the search proceeds to the first location of the table. And this is the reason why this technique is known as closed hashing. Also, one thing you must have observed while explaining the algorithm, I pointed out that the indices will be searched one after the other. Now, since the technique closed hashing searches in a straight line, it is also alternatively termed linear probing. Here, the word probe means to search. So the word probe means search. Okay. Now, let's look at this example. Let's say we have been given a hash table of size 10, and we have the indices of the hash table ranging from 1 to 10. We can have two cases. Either the indexing can start from 0 in that case, the last index would be 9. And if the index, as you can see here, starts from 1, then the last index would be 10. The value of h, which is given to us, is 7, a prime number. And as you can see that it does not match with the size of the hash table. This is very much possible. Now, the hash function which is used is the division method. So with this in perspective, I'll show you a few keys and how they will be mapped to a hash table. Let's take a look at this example. So we have been given a set of key values and we have to apply the division method and see how these values are mapped to our hash table. This set of locations that you see here represents our hash table. So from the information that is given here regarding the size of the hash table, the value of h and the indices, as well as the fact that we are using the division method will give us the exact form of the hash function. So how will I write my hash function? I'll write my hash function as, let's say I'm denoting it by h, and for a particular key value, let's say small k, the formula is k mod h plus 1, right? This is the formula. Why is it plus 1? This plus 1 is because our index starts from 1. The hash table index starts from 1. That's why we have this plus 1. And here small k represents a particular key value from the set of keys. And also the small h that we see is the h value which has already been given to us. So with the information given to us, we can easily find out the hash function. Now what we'll see is how each of these key values map to the different locations. So let's start. Let's plug in the first key, which is 15. So what will be h of 15? See, if I apply the hash function on my key value 15, I'll get 15 mod, what is h? H is 7. So I'll say 15 mod 7 plus 1. Now remember that the mod operation will take place first and the result of the mod operation will be added with 1. And here what does mod represent? Mod represents the remainder. Mod represents, let me write it somewhere else. Let me write it here, okay? So mod represents the remainder of dividing, mod represents the remainder of dividing our key value k by the given value h. Okay, so that is what mod represents. So this is what this mod operator is all about. Okay, now what will be 15 mod 7? So if I divide 15 by 7, I get a remainder of 1. And if I add it with this 1, I will get a value of 2. I'll get a value of 2. So my key 15 will map to the location 2. So let me just put it here. So I'll put 15 in location 2. Now let's move on to 11. Now again, if I apply the hash function on my key value 11, what will I get? I'll get 11 mod 7 plus 1. So what is 11 mod 7? So if I divide 11 by 7, I get a remainder of 4. If I add that with 1, I get 5. Now I can see that location 5 is empty. So I can directly place my key value 11 inside it. Now the next key value is 25. The next key value is 25. Now if I take 25, if I divide it by 7, what is the remainder that I get? So what is 25 mod 7? So 25 mod 7 is 4. So on dividing 25 by 7, I get a remainder of 4. And if I add that with 1, what do I get? I get 5, right? So 25 mod 7 is 4. Add that with 1, you get 5. Now, this is very interesting. I am using this asterisk because I can see that location 5 is already filled up. See, location 5 already contains 11. And I'm trying to map this key value 25 into my hash table. and I find out by applying the hash function that it is also being mapped to the same index. If you remember from the previous video, I had pointed out that the mapping is surjective. That means multiple key values can be mapped to the same location, and such a condition is known as collision. So we have experienced the first collision for the given set of values and the given hash table. Now, what is the collision resolution technique that we are employing? We are employing the collision resolution technique of closed hashing. And what does the closed hashing algorithm tell us? The closed hashing algorithm tells us that you look at the point of collision and you label it as I. So what is the point of collision? The point of collision is index 5. So I will mark it as my I. I'll mark it as I. Now I'll start a sequential search operation from the next location of the point of collision. So the point of collision is I, and what is the next location of I? The next location is I plus 1. So that means 5 plus 1, 6. Now I'll go to location 6, and what will happen? Like you can see, I've listed out 3 cases. So what are the possibilities if I go to the next location? Either I'll find the key is found. That means 25 is already present in location 6. Does location 6 contain 25? No, it's empty. So we'll look at the second case. What is the second case? An empty slot is found. Yes, location 6 is empty. Now, since we have found an empty slot, our search was unsuccessful, and we can simply take our key value and place it at this location. So we'll place it at location 6. After this, we'll take the next key value. What is the next key value? The next key value is 16. Now, if I apply the hash function on my key value 16, so I'll say 16 mod 7, and I'll add it up with 1. So what is 16 mod 7? 16 mod 7 is what you get on dividing 16 by 7 as remainder. So on dividing 16 by 7, the remainder that we get is 2. And if we add that with 1, we get 3. Now if we look at location 3, it's empty. So I can simply take my key value 16 and place it at location 3. Next, we'll move on to the next key value, which is 9. Now, if I apply the hash function on the key value 9, what will I get? I'll get 9 mod 7 as 2, and 2 plus 1 is 3. And again, this is a case of collision. Why? Because the third location is already filled up by the key value 16. So I cannot place 9 at this location 3. What will I do? I'll apply closed hashing. So I'll apply linear probing or closed hashing and start a sequential search from the next location of the point of collision. So the point of collision in this case is index 3. So I'll start from the next location. So I'll start from the next location following the point of collision. So I'll start from 4. Now I can see that 4 is empty. So my second case has occurred, and the second case tells us that since it is an empty slot, you simply take your key value and you place it there. So I'll place my key value 9 in the location 4. And the next key value that I have to look at is 8. Now if I again apply the hash function on the key value 8, what will I get? I'll say 8 mod 7 and I'll add it with 1. So on dividing 8 by 7, the remainder that I get is 1. So 8 mod 7 comes out to be 1. 1 plus 1 is 2. So the result is 2. Now we'll look at location 2. Yes, location 2 is already filled up. So again, this is a case of collision. We'll again apply closed hashing to resolve our collision. So we'll start the sequential search from the next index following 2. So which is the next index following index 2? Index 3. So I'll start the search operation from index 3. What will I check? I'll check whether 8 is present or not. Is 8 present in location 3? No. Is 8 present in location 4? No. Is 8 present in location 5? No. Is 8 present in location 6? No. Is 8 present in location 7? No, but location 7 is empty. So I'll simply take my key value 8 and place it at location 7. Right? Now, my next key value is 12. So again, I'll apply my hash function. I'll just lift this up a bit. Yeah. So I'll apply the hash function on 12 And what will I get? So if I apply 12 mod 7 and if I add it up with 1, so 12 mod 7 gives me 5 and 5 plus 1 gives me 6. Now if you look at location 6, it's already occupied, so it is a case of collision. Now since it is a case of collision, I have to resolve this case. And how do I resolve it? In this case, I'll apply closed hashing. So I'll start from the next location following 6. So I start from 7, a sequential search. The key is 12. Does 12 match with the key present in location 7? No, it doesn't. So I'll go to the next location. Does 12 match with the content of location 8? No, but location 8 is empty. So I'll simply take my key value and place it there. So I'll place it here, right? And the last key value that we have been given is 8. So let me apply the hash function on 8. So what will I get? So if I apply 12 mod 8 plus 1, what will I get? So what is 12 mod 8? 12 mod 8 comes out to be 4, and 4 plus 1 is 5. So what will we do? We see that location 5 is already occupied. It's occupied by 11. So again, this is a case of collision. We'll have to resolve it using closed hashing. So we'll start from the next location following the index of collision. The index of collision is 5. So the next location following the index of collision is 6. So I'll check. What is the content of location 6? 25. Does it match with my key value 8? No, it does not. So I'll go on to the next location. In the next location, I find that there is a match. See, the key value 8 is matching with the content of location 7, which is my current location of scan. So what will I do? I'll report that search is successful and there is no need to insert this key value in the hash table since it is already present there. So from this example, what can we conclude? We can conclude that while inserting these keys and using the process of closed hashing as collision resolution, we ended up getting 1, 2, 3, 4, 5 collisions. So we ended up getting 5 collisions. Now let's move on to a few more features of closed hashing. Closed hashing, like we saw in the previous example, is very simple to implement and very easy to grasp. The concept is very intuitive in nature, and its algorithm employs sequential search, which is also very easily implementable in a computer using programming. But it has one major drawback, and that drawback is primary clustering. What do you mean by primary clustering? Let me just bring up the previous example for you. So if you look at the previous example, what you saw at one point, let's say, you saw that, or as you can see, even in the final hash table, the values, more than half of the values are distributed across the middle portion or are distributed across one particular segment of the hash table. I'll repeat this point. You can see that the key values are clustered in large groups, and as a result, sequential search becomes slower and slower. And this type of clustering is known as primary clustering, where you have, again I'll repeat, the key values being stacked up or being clustered only across few continuous segments of the hash table. There is no uniform distribution. Like this is although the final configuration of the hash table. While building up the hash table, you must have seen, even if you rewind the video, let's say 4 to 5 minutes back, you would have found that this particular portion was mainly being crowded. So more than half of the key values are being placed at one particular segment of the hash table. Now this, what happens is, this increases the time for sequential search, and this problem is known as primary clustering. So what are the solutions to primary clustering? The solutions are, as you can see, random probing, which employs a pseudo-random number generator. You can also go for two hash functions in the technique of double hashing, also known as rehashing, or you could go for quadratic probing, in which instead of searching the hash table in a linear fashion, you skip locations iteratively and look for the search item or an empty space to resolve collision. Now, what I'll do is I'll explain what is random probing. Random probing uses a pseudo-random number generator to generate a random sequence of locations rather than an ordered sequence as we saw in the case of linear probing. The random sequence generated by the pseudo-random number generator contains all the positions between 1 and h, where h is assumed to be the highest location of the hash table. An example of the pseudo-random number generator is what you can see here on your screen. Now this produces a random sequence of locations where I is a number in the sequence, m and h are integers which are relatively prime to each other. And also one thing that you must keep in mind is that the h that you can see here is the highest location of the hash table, and indexing in this case has started from 1, and that's why you have this plus 1 at the end. If the indexing were to start from 0, you wouldn't have required this plus 1. So the pseudo-random number generator would have looked something like this. Now, what I'll do is I'll take an example where I'll show you how random probing resolves the problem of primary clustering. Okay, so the example that you can see here has taken a value of 5 for m, a value of 11 for h. Now, the value of 11 for h denotes that the highest location of the hash table is 11, which also means that the number of locations in the hash table is 11, which also indicates that the size of the hash table is 11. And the initial number of the sequence that we are considering, the random sequence that we will be generating, the initial number that we are considering is 2. Here 2 could mean the point where collision takes place. Now from here onwards, now in linear probing, what would you have done? You would have checked for location 3 followed by location 4, 5, 6 and so on till either of the cases that we saw were satisfied. That means either the key is found or an empty location is found, or we come back to the starting point of our search. Here what you will see is we will generate a random sequence which will denote the order in which we should probe our hash table. So let's see the sequence being generated. So the formula, I'll just use this formula. So I, what is I? What will be the next? Here I denotes the next number in sequence. That means the next location that I should look for in my hash table. So how is it found? It is found by the current value of I. The current value of I is 2. What is the value of m? The value of m is 5. So that's 2 plus 5. Mod 11 plus 1. What will I get? I'll get 2 plus 5 is 7, and 7 mod 11 is, of course, 7. If you divide 7 by 11, the remainder that you get is 7 itself, because it is lesser than the mod value. And what is 7 plus 1? 7 plus 1 is 8. So if you're starting from location 2, let's say location 2 was your point of collision, then the next location that you should probe is 8 and not 3. Now, if you find that location 8 is already occupied, then what is the next location that you look at? The next location that you should look at will be found again from this formula. So what is the current value of I? The current value of I is 8, because it has changed, right? I applied this formula and I found that the value was 8. Now, in order to find the next location that I should probe, I should place 8 in place of I. And I'll apply mod 11 and I'll add 1. So what is 8 plus 5? 13. What is 13 mod 11? 13 mod 11 is 2. And what is 2 plus 1? 2 plus 1 is 3. 2 plus 1 is 3. So after 8, the next location that we should probe is 3. Again, if I find that location 3 is occupied, then the next location that I probe is not 4, as I would have done in case of linear probing, but I would use this random number generator to find the location. So I would say 3 plus 5 mod 11 plus 1, and what will I get? What is 3 plus 5? 8. What is 8 mod 11? 8. And what is 8 plus 1? 9. 9. So that means after location 3, I should probe location 9. So in this way, if I generate the remaining sequence, what would I get? I've written down the probe sequence that we should follow. So as you can see that, where do we stop? We stopped when we came back to location 2. And what is location 2? Location 2 was our initial point of search. So if you remember the 3 cases which I had mentioned, what were they? Let me bring them up for you. So the 3 cases were either the key is found, or the empty slot is found, or we come back to the starting point. If we come back to the starting point, we have to stop our search procedure and conclude that the hash table is full and there is no place where we could insert a new key value. So when will you stop generating the sequence? You will stop generating the sequence when you come back to the initial point. And see, what was the size of the hash table? The size of the hash table in this case is given by h, and it's 11, and we have managed to probe all 11 locations. See, we started off with 8, 3, 9, 4 and so on. We came back to location 2. So we were successfully able to probe all locations of our hash table using this pseudo random number generator. In case of linear probing, what would we have done? We would have started from 2, moved on to 3, then 4, 5, 6 and so on. But here we have traversed all locations of the hash table, but not in a sequential manner. This random searching or this random visiting of all locations in the hash table avoids the primary clustering problem. So remember, we can avoid primary clustering if the probe follows the said random sequence, the given random sequence which we have successfully generated. So I hope you have understood the points which I have discussed in this video of part 2 on hashing. In the next video, we will discuss double hashing and quadratic probing. I'll see you in the next one. Please feel free to leave your doubts in the comment section below. Thank you.